everyone. So this is the last question in the 2019 Set 1 free response questions. As always, make sure that you work on the questions yourself. The link to the question set will be in the description below. All right. So this third question is the rotation question. So let's just jump right into it. Now, the first question is basically derive an expression for the angular speed. Make sure that you solve in terms of this I, R, D, F, and T. So one thing that I would, if you remember, one of the things they said was to try to think about how you would solve this question without the whole rotation stuff. So essentially what we have is an object with some mass. It's starting from rest and it's getting a force exerted on it, and we want to know what the final speed is. So normally what we would do is to find the final speed, it would be final equals the initial velocity plus AT. In this case, the initial velocity is 0. We would use force to find the acceleration, so we can use F net equals ma and say that this is just force times time over mass. And that would be my answer. I'm pretty much doing that same exact setup, except what I'm going to end up doing is changing everything to their rotational terms. So V would end up being an omega. F will end up being, that will end up being a torque. The time is the same thing, so that's still time. And mass is going to be that rotational inertia. If you want to actually know the equations that we would do omega equals omega naught plus alpha t. Once again, this is 0, so it's final velocity, or final angular velocity is the angular acceleration times time. I can use torque is equal to I alpha. Alpha equals tau over I. So that's where I'm getting this. When I plug this in, I get tau t over I. I can take this one step further and say that tau is going to be force times the radius. I'm going to want to be careful here. I want to choose the distance the wheel is, or the force is acting from the axis. So I'm not going to put R here. I'm going to put D. T over I. And that ends up, I believe that's going to be my answer. Probably delta, I probably end up changing this to delta t, like that. And that should be it. The only thing I can actually think of, I probably should put the little subscripts on here. So that should be a little p, and that should be a little p to represent platform. But besides that, everything else is correct. So this was a 2-point question. There is basically 1 point for this line and 1 point to get the answer, or I should say doing these two things together. So this is 1 point, this was 1 point. Like I said, doing this is a really good way of kind of getting an idea of what the equation should look like, but it doesn't really replace doing the actual work. So you would still have to do the rotation equations. Okay, so the next part, part B, says determine an expression for the kinetic energy, blah, 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 when it reaches the speed. So what I can do is, honestly, I think the easiest one, not too difficult, is just going to be doing rotational speed. Rotational kinetic energy is 1/2 I omega squared. Plug the numbers in. 1/2 I times IP. This is F d delta t all squared. So this will end up being, the F stays squared, the D is squared, the delta time is squared, and then the IP was squared, but since there was an IP in the numerator, that cancels out one of them. So it'll end up being equal to this. So this was another 2-point question. 1 point for this, 1 point for that. Easy enough. All right, so part C says they want the angular speed omega w when the platform has reached angular speed this. Okay. The omega that they're referring to is, or the omega w, the wheel that they're referring to is this. So they want to know what the speed of this object is. So we know that because this is rotating without slipping, we know that the speed of these two are going to be equal. So we know that the speed, the speed of the linear speed of the platform. Sorry, the linear speed of the platform is going to be equal to the linear speed of the wheel. Because what that means is that since they're not slipping, if I pick a point on the platform, it's going to be in contact with the wheel, and they're going to move together linearly at the same rate. If they weren't moving at the same rate, then the wheel would be slipping essentially. That one of them is going to be moving faster than the other, can rotate. So we know the linear speeds are going to be equal, which means that I can do. Let me try and make sure I write this clearly. RP times omega p is going to be equal to RW omega W. So the radius of the platform, or at least where the wheel is going to be the capital D. I know what, it says actually solve in terms of angular omega p, so I can just leave that as is. The radius of the wheel is going to be R. So we will end up getting is that the angular speed of the wheel is the angular speed of the platform times by this ratio of their radiuses. And this was a 2-point question. 1 point for this, and 1 point for basically all this. All right, let's move down to part D. So part D this one's actually another really standard question. So we had the platform spinning, and then we drop the platform, another platform on top, and we want to know what their new thing is. This is essentially conservation of momentum, or in this case, angular momentum. So I'm going to say the angular momentum of the two are equal. Initially, the platform is the only one moving, so this is going to be the initial angular momentum of the platform is equal to, they're going to end up moving together, so I'm going to call this, I'm just going to say it's LP plus L. Let's see, I'll just call it 2 right there. So this one is going to be the I omega, so this would be I P omega P. This is just like with regular momentum, where we would have added their two masses. Like we would have essentially had this as our equation, m plus m times the final speed. I'm doing the same thing here. I'm just going to use the rotational inertias. So IP plus, it has the same rotational inertia, so this one's going to be another IP. And this is what I'm looking for. So this will end up being IP omega P equals 2 IP omega F. 2 IPs cancel out. So omega F is equal to 1/2 omega platform. Which again makes sense with the linear case, if these masses were equal, I would have had the same thing, that the final speed was equal to whatever half the original speed was. You essentially got 1 point for either of these two comments, and then 1 point for this part. All right, let's go down here. Okay, so they give us this graph, and then there's a few other questions down below. So this is basically a graph of all the different final speeds relative to the initial speeds. Okay. And the object that they're dropping on is unknown. That's the other thing. All right, so let's see. They want us to draw a line of best fit and then use this to find the rotational inertia of the unknown object. So the line of best fit's easy. It's going to look like this. Yeah, I guess that's good enough. I have some points above, some points below. Might actually want to tilt this a little bit. There we go. Now, in order to find this rotational inertia, I actually kind of want to fool around with the equation first. So if we actually look back to this previous question when we did this, I'm going to rewrite this. So this was IP omega I equals IP plus IU omega F. So the equation I have is omega F versus omega I. So if I actually clean this equation up, and I'm going to rewrite it so it looks like this. This would have been IP divided by IP plus IU omega I. I now have this written in the form of y equals mx. My final angular velocity is y. My initial angular velocity is x, which means that my slope is going to be equal to this ratio. So I know that if I take the slope of this line, I can set it equal to this. The key thing here is I cannot use any of these points. So even though I probably could have drawn this so that I crossed two of these points, I do not want to do that. I don't want to use them. So instead, I need to find points that this my line crosses. So there's a point there. And let's find another point. Right. Oh, wow. Drew my line pretty well. So slope is equal to change in y over change in x. So the y values, this is going to be 4 minus 0.2. This goes all the way up to 9.5. And this will be 0.5. So this is 3.8 divided by 9. Plugging that in, 3.8 divided by 9 will end up getting me a slope equal to 0.42. And like I said, I'm going to set this equal to this ratio, IP divided by IP plus IU. Cross multiply basically means that IU is going to be equal to IP divided by this slope 0.42 minus IP. I know that IP is 3.1. So 3.1 divided by 0.42 minus 3.1 is going to get me a rotational inertia of 4.28. Sorry. All right. So altogether, we end up having this line of best fit was worth 1 point. Over here, you got 1 point for pretty much getting to doing this line. So it's actually kind of weird how they do it. Um, this entire section where I said that the slope was equal to this was 1 point, and then doing the slope and getting this answer was another point. So they actually kind of did it a little bit differently, but you probably still would have been using the same idea. All right, part F. The kinetic energy of the platform is equal to Ki. They want to know about the other. What is this? Okay, so they want to know about what's going on with the kinetic energies. Is it going to be greater than, equal to, or less than? So there's a few different ways to go about this to get rid of stuff, but I'll tell you now that this is not an elastic collision. This is what we call an inelastic collision. In fact, this is actually a perfectly inelastic collision. So the answer is going to be that the final is less than Ki. So you can, there's a few different ways to say this, but essentially what you want to do is make some sort of comment that this is an inelastic collision. The objects, pretty much a very quick reason of why it's an inelastic collision. Um, and the fact that when it's an inelastic collision, the kinetic energy decreases. If you remember, there's really only two collisions or two setups. There is going to be, so if the kinetic energy is greater than Ki, this is what we consider an explosion. This is one where the objects are essentially connected. They start together and then they split apart because of some stored potential energy, stored spring energy, chemical energy, something that is used to kind of separate them. In that case, we could have the kinetic energies actually changing because we have energy being added into the system. Um, then we have this one, which is a perfectly elastic collision. And then this would be a perfectly inelastic collision where this one actually also is inelastic. I should probably mention that. But this would be a perfectly inelastic collision where they're sticking together. All right, so those are the three collisions, and we just had to figure out which one our collision was, sticking, and then state why. Okay, part G. Let's see. They mention that the center of masses don't actually align, and they want to know whether or not this IU will end up being greater than, less than, or equal to the actual unknown setup. Oh, so the answer to this is going to be greater. Now, there's a few different ways of doing this, but one of the things is that the this is something that I believe we mentioned in AP1. It's called the parallel axis theorem. Basically says that the rotational inertia of this system, that now that we have this object being placed like here, and it's rotating in this off balanced way, so that the center of rotation of the platform isn't really lined up with this, what I can do is I can say that the rotational inertia of this object is going to be equal to the rotational inertia around the center of mass plus the mass of the object times some value r that it is from the actual center of rotation. So basically, the difference between the actual rotational inertia and the rotational inertia we calculated is going to be off by this factor. And that's pretty much it. So if we want to figure out what the actual rotational inertia is, we would have to end up subtracting the actual mass of the object times by the distance their centers were. This was another 2-point question. So you got 1 point for mentioning the greater than part and 1 point for basically mentioning this parallel axis theorem. I don't think I mentioned the points for this one. This one was another 2 point, 1 point for this, and then 1 point for this statement. All right, and that's it for this question. So feel free to let me know if you have any questions. Otherwise, good luck and have a great day.